Hello everyone, welcome to Mathematical Technical Workshop. Topic 1, three-dimensional figure, episode 1. A three-dimensional figure is a geometrical figure which has three dimensions, including length, width, and height. These three dimensions are kinds of just length. It's just a length, the distance from one point to another. And the terms used in three-dimensional figure are as follows. We have terminology number one, a point. A point is a dimensionless figure, as you can observe there. But a line is a figure with one dimension. It's a figure with one dimension from one point to another, as you can see here. This is just a line. And we have another term, a plane. A plane is a geometric figure with two dimensions. I mean the length and the width. Or sometimes we can have a height and the length, but all of them, we can term them as length. But now a plane, it just look like its boundary, it forms a region. Yeah, its boundary can form a region, as you can see here in the rectangular shape, and this in triangular face. The other term that we have is a solid figure. A solid figure is a geometric figure with three dimensions, namely the length, the width, and the height. And a solid figure is a figure that we can put something inside and can just stay inside because it has a volume. And examples of solid figures including the cuboid, which is the prism, and the pyramids. These are solid figures. Three-dimensional figures have been grouped as polyhedrons and non-polyhedron figures. When we say polyhedron figures, the solid figure or three-dimensional figure formed by flat faces or the plane surfaces. For example, prism and pyramids. These are polyhedron figures. When you observe them like here, the pyramid and the cube, all the faces are flat. So they are not curved ones, so they are flat. That's why we call them polyhedrons. Non-polyhedron figures, these are three-dimensional figures formed by curved surfaces. They're formed by the curved surfaces, I mean the circular faces, including cone, as you can see cone here, the faces, the base is circular in nature, as you can observe the other faces which are curved one, and the cylinder, the same apply. You can see two bases which are parallel and congruent, and they are circular in shape, and we have the folded part between the two bases which are curved. And also we have the sphere, which is a perfect roundy shape figure. So these are non-polyhedron figures. They are not formed by the flat surfaces. Now, when we switch to the polyhedrons, we have two typical examples of polyhedron figures, including prisms and the pyramids. Prisms are the solid figures with the two congruent and parallel bases. In every prism, we have two bases, and these bases are parallel. That means they never meet. And these bases are congruent, means they are the same. And the prism now, it is formed by the flat surfaces, but their bases can be any polygons. I mean, can be triangular shape, can be rectangle or quadrilateral, can be pentagon, hexagon, whatever. Any polygon can be a base. But the other remaining faces, which are not base, which we can term them as lateral faces, these are rectangular in shape. Now, we have a special prisms like cuboid. Cuboid is a prism whose base is rectangular in shape, and the square prism, we can also call them cube. Is a prism whose base is a square. And normally when we name the prisms, we name according to the shape of their base. If it is pentagon, we name them as pentagonal prism. If it is triangle, we can name them as triangular prism because the shape of the base is that polygon. Now when we step on the pyramids are also polyhedron figures, but with one base, and they are formed with the flat faces, as we said earlier. And the pyramids, the base can be any polygon, but the other remaining faces, which are lateral, are not base, they are triangular in shape. Hello everyone, welcome back to the second part. of episode 1. Now we are going to see the angles and the planes, and we are going to navigate on the following categories: angle between two lines, the angle between a line and a plane, angle between a line and a plane, but also angle between two intersecting planes. Also, we'll see the surface area of the solid figures and the volume of the solid figures. Now, by starting, let's see this example here. Given a figure below, as you can observe the figure that is polyhedron, prism, and the dimensions are 8 centimeter by 6 centimeter by 4 centimeters. Now we are told to calculate the following: angle between lines AD, as you can observe from the figure, and AH. Also, case B, angle between a line AG, a line that is formed by the endpoint AG, and the plane ABCD, which is the base of that prism. Also, we are told to find the angle between planes. Here are two planes that are intersecting at a certain line. And now we are supposed to find that angle between the planes ABCD, as you can observe, ABCD, and the plane ABGH, which are formed by those vertices. And the case C, we are told to find the case D. We are told to find the surface area of the solid figure, and the last case, we are told to find the volume of the solid figure. Now, by starting with case R, angle between lines A and D. So here, you need to go back to your figure, the prism, the rectangular prism here, and angle between two lines, it means the angle that is formed between the point of intersection of those two lines. We have line AD, as you can observe here, AD, and the other line is AH. So we need to connect point A and H with the end points to form that line segment. So we can connect by dotted lines like this here. So you take your ruler with a pencil. Now you connect the two end points. Now after connecting, we have a line segment AH. Now between the two lines AH and the AD, we can observe the point of intersection that is point A. And from here, this point of intersection is where the angle now is formed. So the angle is formed here at the common point, angle theta. So the name of the angle now will be HADODAH. It means the point of commonness, or the point of intersection between the line, is where the angle lies. So after having now the angle, we need to take the triangle where the angle can be found, or where the angle is formed in that triangle. And the triangle that we are taking here is triangle HAD, which is the right angle triangle at D. Now we can sketch like this one, triangle ADH, as you can observe here. The dimension are 6 centimeter by 4 centimeter. Now, for we to get this angle here, theta, we use the advantage of the given dimensions, 4 centimeter and 6 centimeter there. So this angle, when we try to check the side opposite to the angle, this will be the opposite side, this will be the adjacent, and this will be the hypotenuse. Because we have opposite and the adjacent side, we can use trigonometric ratio, which is tangent. So now we take tan of theta equals to the opposite, the ratio of the opposite side to the adjacent side from the right angle triangle, HAD. Now, the opposite side by dimension will be 4 centimeter, as you can observe here, and the adjacent side is 60 centimeter, as observed there. So when we cancel out centimeter and centimeter, because these are the ratio, we compare the same quantities, so these units will cancel out. Now we remain with the 2/3 after simplifying with the factor 2. By 2 here to 4 we get 2, and when we take 6 divided by 2 we get 3. Now from here we need an angle, so we need to find the tan inverse of these 2/3. So theta now will be equal to tan inverse of 2/3, which when you perform to our calculator here, yeah, it is 33.6900 degrees, or when we express it in degree and minutes, we'll have 33 degree by 41 minutes. So now the size of our angle now DAH will be equal to 33 degrees by 41 minutes. And this now will be the angle that is formed between the lines AD and DAH. Okay, let's now go to case B. We are required to find the angle between a line AG and the plane ABCD. Now from the prism here, our cuboid, AG we can observe here, point A is here and the point G is here. When we connect the 2 points, we can make a line AG by the dotted line, as you can see in blue color. But also the plane ABCD, you can observe from the red color, ABCD. That's the base, that's the plane. So what is the angle now is formed between the line AG and the plane ABCD. By starting now, we'll start with the definition of the angle between the line and the plane. The angle between a line and a plane is the angle that is formed between the line itself and its projection on that plane ABCD. So how do we start now formulating the projection of the line AG on the plane ABCD? The first thing that we are going to do, we are going to find the line, the point of intersection between the line and the plane. So we can use a technique like you write the line AG and the plane ABCD. Now it can be observed like that. From there, we note the point of intersection, the point that is common. It's found in the line and also it's found in the plane. A line, you can understand the line by, a line is formed by 2 points, but a plane is formed by points starting from 3 to 4 and so on. So from here, point A is common one. So from point A, the point of intersection between that line and the plane, and we can note it here. Now, the point that is remaining on the line, we know it is point G. From that point G, we can use it to make its projection or to formulate the normal line to the plane, which is very perpendicular. And now we can use the technique of placing a torch overhead. So when you place a torch here, and we just place here because the base is down, so the shadow of G can fall on the base, which is the plane now. Now the shadow of G will fall on the point C, or we can say the projection of G is on C. Now after having the projection of G, which is C, we connect that point of intersection with the projection of point G. And now we'll form the line AC. So we can just draw here by red line AC. So we join by dotted line, can have AC. Now AC is, this is the orthogonal projection of the line now AG on the plane ABCD. It means here it is just form a right triangle there. So AG now, it is the shadow or the projection of AG. Now coming back to the definition of angle between a line and a plane, thus is the angle between the line AG itself and its projection AC on the plane. So the angle is formed here at the point of intersection, point A. So our angle now is GAC. That will be angle GAC. So the angle is GAC, or we can say angle A, angle C, you can say angle CAG. Now, from the name of that angle, we can use those points to form that triangle, the triangle that the angle belongs. So from there, we can say from the triangle GAC, which is the right angle with the triangle here, GAC, the right angle with the triangle T, the right angle here is C, and here now is our G, and here the point A where the angle is. Now, another thing that we are going to look here are the dimensions. Now, AC we don't have, but we have this dimension from the figure AD, which was 60 centimeter, AB, which was 80 centimeter, and the HD, which is a height, which is 4 centimeters. So we are lacking dimension like for AC and the AG. So HD the same as CG. So here it is also 4 centimeter. So what is important here now, we need to find the length AC, whereby the length AC is the diagonal of the base. You know, our base is rectangular in shape, and always rectangular shapes, they have two diagonals. So diagonal AC and BD. But here, when we find AC, by the advantage of this length and width, we can be able now to find this angle here, because we only need one dimension from this triangle. So by starting, we start finding the diagonal AC. So now we can draw here again the base. This is our base. That is rectangular in shape. So we have A, B, C, and D. But the diagonal here, AC, is what we are looking at. The diagonal AC. Now AB is 8 centimeter, and BC the same as AD, which is 60 centimeter. Now by Pythagoras theorem, we can apply to find the AC, which is the hypotenuse now. So by Pythagoras theorem, we can say AB square, when we plus BC square, is less more to AC square. So AB, it is 8 square, we plus BC, which is 6 square, equals to AC square. So from there, 80 square, we get 64, we plus 60 square is 36. Now AC square equals to 100. So when we find now, on squaring both sides, we can have something like this. So AC now will be equals to 10 centimeters. So now AC, we know it is what? 10 centimeters. So now we can move back to a triangle. That is the triangle where the angle is GAC. AC here is 10 centimeter. But the other dimension, GC the same as DH, which is 4 centimeters. Now from there we have two dimensions, so we can use trigonometric ratio because we have two sides. Now we can say this side faces by the angle is the opposite, and this will be the adjacent side. So from trigonometric ratio, which is opposite of adjacent, which is tan. So tan theta now equals to the ratio of opposites and to the adjacent side. Our opposite here is 4 centimeter. Adjacent here is 10 centimeters. So tan theta will be equals to, when we cancel out these units, we'll have 4 out of 10, which is the same as by 2 is 2, by 2 is 5. So we'll have tan theta equals to 2/5. Now theta, for we to get theta now, we need to find tan inverse, or the arctan of 2/5. So theta now will be equals to what? Now, through calculator, tan inverse of 2 now equals to, it is 28.8014 degrees, or 21 degree by 48, 21 degree by 48 minutes. Now, theta was representing the angle GAC or CAG. So we can conclude now by saying the angle between the line AG and the base and the plane, which is the base ABCD, is as 21 degrees by 48 minutes. And that now will be the angle between the line and the plane, which is the angle between the line itself and its projection on the plane, or its shadow on the plane, as you can observe from the diagrams. Thank you. Let's see case C. Case C. The angle between planes ABCD and the ABGH. So when you see the more than 3 points, I mean the vertices, that means a plane. So this is the plane with the 4 sides and the plane with the 4 sides. So what the angle now is formed between the 2 planes. So we need to know the definition of the angle between the planes, 2 intersecting planes. The angle between 2 planes is the angle that is formed between 2 perpendicular lines from every plane at the line of intersection at a point. It means that point is found on the line of intersection. So from the figure here, the prism, we need to develop the line of intersections, and we need to develop at every plane. Plane A, B, C, D, we develop a perpendicular line to the line of intersection at a point, and the same apply to the plane A, B, G, H, perpendicular line to the line of intersection at a point. So when we start now solving, we need to know the line of intersection. Solving strategy number 1. Line of intersection. Between the planes. And before going direct to the line of intersection, you can observe your figure and note the planes, and even you can see it through observing the figure without even having used the technique on finding that line of intersection. Now we have the plane ABCD, ABCD, and the plane ABGH. So we can use maybe the blue color. So we join ABG. Our BG is here. Joined by dotted lines. And GH. Then coming back to HA. Just use even the solid line. It's not necessary to use dotted, but you can form maybe by using dotted lines. So as you can see the diagrams. Now blue in color, ABGH, and red in color ABCD. So you can observe where the 2 colors intersecting, red and the blue, is where the line of intersection is. If that cannot be applied, we can take the planes now. So this is the plane number 1, plane 1, that is A, B, C, D. And here we have the second plane, that is A, B, G, H. Now we can note the point of intersection, the point that is found in one plane and the same that is found in the second plane. Point A, point B, B. So now these 2 points, A and B, they form a line of intersection. So the line of intersection is the line AB. It's a line segment AB. And you can see here from the diagram, that's the line that where the 2 colors intersecting, A and B. Now, after having noted the line of intersection, you can just extend it. So as you can see it clearly by the dotted lines, extending it like that. So at this line of intersection, which has 2 points, A and B, now we need to develop perpendicular lines from these 2 planes, from plane A, B, C, and D, and A, B, G, H. We need to develop perpendicular lines. Now, having said that, solving strategy number 2, we can use now the one technique. This one technique will help us generating perpendicular lines from each plane. One means which one among the given points is nearest to the point of intersection to the point that is found on the line of intersection. Now, you just check the point that remains after crossing the intersected point or the common point from the two planes, the point that remains. Here in plane 1, it remains point CD, and in plane 2, it remains point GH. Now, at these 2 points, we can start with any plane, either plane 1 or plane 2. Now, by starting maybe with a plane 1, that is A, B, C, D. So the point that remains after crossing the common point is C, D. Now, from C and D, you choose one point. Maybe we choose D or we choose C. Maybe now we can choose C. But you are free to choose any point because the angle can be formed here at point B, or can be formed at the middle, or can be formed at this point A. And all these angles will be the same in magnitude. So what we do is just a matter of choice. So we can choose point C. So when we choose C here, this now will be the first point in plane ABCD that will form perpendicular line to the line of intersection at point B. So it will be like this. So from C, now you draw a perpendicular line to the line of intersection now to point B. So when we say at the point, that's point B. So it means the angle now will be formed at this point B and not point A, because this now will be the chosen point. So what next? So this will be the first perpendicular line, BC or CB, to the line of intersection at B in this plane 1, ABCD. So now we'll have the second perpendicular line from the plane ABGH, which is GB. As you can see here, it is perpendicular to the line of intersection at point B. Now, what is the angle between the two planes now? Is the angle that is formed between two perpendicular lines from every plane. That is to say, CB and the other line is GB at the line of intersection at point B. So our angle will be here. And this now will be our angle, theta. So the name of the angle now will be CBG or GBC. Now, from that name, we can use the advantage of the name of the angle to find that triangle, and then we calculate the size of the angle. So now we can say the angle formed is the angle CBG, and it is found in this triangle CBG. So we can say from triangle CBG, now we can sketch it. The triangle CBG. Now the right angle is here at point C. So here is G, and here is the point B, where now our angle is. Now we are going to see the dimension now, so as you can calculate the size of the angle. CB is the same as DA, which is 6 centimeter in magnitude, and the GC is the same as HD, which is 4 centimeter, the height, 4 centimeter in magnitude. Now we have advantage of two size dimensions. Now we can calculate the angle from trigonometric ratio. So this is the opposite side, adjacent, hypotenuse. Now we use opposite and adjacent because the dimensions are known. So we can go to tangent. Tan theta equals to the ratio of opposite side dimension to the adjacent side dimensions. Now opposite is 4 centimeter and adjacent is 60 centimeters. So tan theta equals to, when we simplify, here will be 2, 6 divided by 2 we get 3. So theta equals to tan inverse of 2/3. So when we find through calculator, tan inverse of 2/3 now is less more to 33.690 1 degree, or we can say this equals to 33.69 degree, or when we change to degree and minutes, will be 33 degree by 41 minutes. So we say now the angle between planes A, B, C, D, and the other plane is A, B, G, H, is 33 degree by 41 minutes. So this will be now the magnitude or the size of our angle, and that will mark the angle between our two planes. Thank you. Okay, now we are going to see case D, which we are required to find the surface area of the solid figure. Now our figure here is a prism A, B, C, D, E, F, G, H. That's a prism. On calculating the surface area, the first thing we need to know all the faces that are found in the three-dimensional figure, this box here, or we call it a cuboid. Now we have 6 faces, as you can observe, 2 on the sides, then we have front one, the back one, then we have 2 bases, the bottom and the top bases. So that's making a total of 6 faces. So we need to find the surface of all these faces. Then when we total them, we get the surface area of the whole prism. So what we do now, this can be calculated formula-wise. Solution. Surface area is given by, now the faces, you can see we have 2 pairs of faces which are equal. The front and the back, the sideways sides, the faces are the same, and the top and the bottom, which are the bases, which are congruent and parallel. So what we do, when we are dealing with the faces, we take 2, because they are 2 in number, I mean pair, then length times the width, because here we are dealing with the rectangular faces. So for example, A, B, F, E. This is the length, the width. That's why we say length times width. Now we add 2 again. Then now, this front and the back will represent that one. But now coming to the sides, the side faces, we have B, F, G, C, and A, E, H, D. So here we have the width. This will be the height, the length, the width, yeah, something like that, H. So all these vertical lines will be height, but all these A, D, B, C, G, F, H, E will be the width. And these now, all these horizontal lines will be length. I mean A, B, E, F, H, G, yeah, and the D, C will be the length. So what do we do? We're coming back to the side faces. So we take width times height. Width times height. Now we plus 2. Then now we come to the bases. The front and the back faces. That is length times height. Length times height. Or the simplest way, because we are dealing with 3 dimension and it's a solid figure, when we find the surface area, it's the same as saying length goes with the width, then length again goes with the height, and now we check length has shared with the width and height. So what remains is width and the height, these ones. So you can have the formula. Now because the faces are pairs which are congruent and parallel, it means now we say 2, then 2, and here will be 2. So when we add all of these now, we get the total of all the faces. So that one also will be a technique. But this is our formula now. Okay, so the surface area is given by the formula. It is 2 brackets length times width. We plus 2 brackets width times height, and we plus 2 bracket length times height. It means now this will mark the totality of all the 6 faces found in the prism. Now on the details, our length here is less more to 8 centimeters. The width equals to 6 centimeter, and the height, which is always represented by the vertical lines, is 4 centimeter magnitude. So now the surface area equals to, now we plug all this information to the formula. So it is 2 brackets, our length is 8 centimeter, we time the width, which is 6 centimeter, brackets we plus 2, we go for the other pair, that is width 6 centimeter times the height, which is 4 centimeter. Now plus 2 brackets, our length is 8 centimeter times the height, which is 4 centimeters. Now, so we start by multiplying the terms inside. So here will be 2 brackets, 8 times 6 is 48, centimeter and centimeter will be centimeter square, we plus, it is 2 brackets, 6 times 4 is 24, centimeter square, we plus 2 brackets, 8 times 4 is 32 centimeter squares bracket. So now we open the brackets by the scalar number 2 outside. So 48 times 2, that is 96 centimeter square, we plus 24 times 2 is 48 centimeter square, we plus 2 times this much, we get 2 times 32, we get 64 centimeter square. So now we operate all the terms. 96 by calculator, we plus 48, we plus 64, so it will be less more to 208 centimeter square. So this now will mark the surface area. So the surface area of the solid, it is 208 centimeter square. Thank you. Okay, the last part we are going to see the volume of the solid figure. Now our figure, as I said earlier, is a prism, cuboid, and we have 3 dimensions, the length, the width, and the height as shown. Solution. So the detail that we have here, we have the length. Our length from the figure is 8 centimeter. We have the width, which is less more to 6 centimeter. And the height, it is 4 centimeter. Now, when calculating now the volume, we use the formula that we find the product of all the dimensions that we are provided with from the figure. So we take the length, we times the width, we times the height. So length is 8 centimeter times the width is 6 centimeter. We time the height, which is 4 centimeters. So on multiplying 8 centimeter, when we take 8 times 6 times 4, we are going to get 192. But centimeter times centimeter times centimeter, this we are going to make centimeter cubic. So volume now equals to 192 centimeter cubic. That's the volume.